All right, let's talk about the absolute backbone of the modern internet. We're going to go deep inside the massive invisible engines that power pretty much every big service you use, the systems that store and serve just a mind-boggling amount of data every single second. Let's get into it.
Seriously, think about it for a second. Every photo you've ever uploaded, every single post, every like, every item you've ever put in a shopping cart, where does it all go? I mean, it can't all be sitting on one giant hard drive somewhere, right? No way. And that simple, kind of obvious thought is the key to understanding one of the biggest challenges in all of computer science.
So here's our game plan. First, we'll see why one server just doesn't cut it. Then, we'll get into the fundamental law that governs all of this stuff. After that, we'll look at how data gets spread out and protected, how all the copies are kept in sync, and what happens when, not if, things break. And finally, we'll put the whole puzzle together. Okay, so before we can understand how thousands of computers work together, we really have to get a handle on why we can't just use one really big one. What are the limits of a single box? So, at the very heart of all this, a lot of the internet's data lives in what's called a key value store. And honestly, it's about as simple as it gets. You have a unique label, the key, and you attach some data to it, the value. You use a put command to stick data in and a get command to pull it out. It's really just a massive, super fast digital filing cabinet. But here's the catch. Even the most ridiculously powerful server you can imagine has its limits. It's going to run out of memory, it's going to run out of disk space, it's just a fact. To handle the insane scale of today's apps, you can't rely on one machine. You need hundreds, sometimes thousands, all working in perfect harmony. And that's where things get really interesting and complicated. The second you start wiring multiple computers together to act like one single system, you slam headfirst into a fundamental law of the universe, at least for distributed computing. It's called the CAP theorem, and it forces every engineer into making a really tough choice. So, the C in CAP stands for consistency. This is a simple promise. Whenever you ask for a piece of data, you will always get the absolute, most recent 100% correct version. No ifs, ands, or buts. Everyone, everywhere, sees the exact same truth at the exact same time. The A is for availability. This just means the system is always on. It always answers your request. It'll never just give you an error because part of it is broken or busy. Its top priority is to be responsive and just give you an answer. And finally, we have P for partition tolerance. Now, a partition is just a technical term for when the network connection between servers breaks. And let's be real, in a world with clumsy backhoes and failing network switches, this is not an if scenario, it's a when scenario. So any real-world system has to be partition tolerant. It is completely non-negotiable. And here it is, the punchline. The CAP theorem proves that you can pick any two of these three guarantees, but you absolutely, positively cannot have all three at once. It's impossible. And since we just agreed that partition tolerance is non-negotiable, well, you do the math. The real choice, the agonizing decision, is always between consistency and availability. And you see this trade-off everywhere. Your banking app, for example, has to pick consistency. You'd much rather see a little loading spinner or even an error than see the wrong account balance, right? But for your social media feed, it's the total opposite. It picks availability every time. It's way better to show you a post from a few seconds ago than to show you a blank screen. Okay, so knowing they have to make this fundamental trade-off, how do engineers actually build these giant systems? Let's open up the toolkit they use to spread out and protect all that precious data. So the very first problem is, how do you decide which server stores which piece of data? Well, the most popular and frankly most beautiful solution is something called consistent hashing. Just picture all of your servers as points on a circle. To figure out where to store your data, you convert its key into another point on that same circle. Then you just walk clockwise around the ring until you bump into a server, and bam, that's its home. It's kind of like musical chairs for data, and it works incredibly well to spread the load evenly. Of course, just storing your data on one server is a terrible idea. I mean, what happens if it dies? So you make copies. This is called replication. Your data isn't just on one server, it's copied to n servers. And n is usually 3. And for maximum safety, you want those 3 servers in totally different buildings, maybe even different cities, to protect against fires, floods, you name it. But making copies just created a whole new problem for us, didn't it?
If you have 3 different versions of the same piece of data, how on earth do you make sure they all stay in sync and tell the same story? The answer is basically a voting system, and it's called Quorum Consensus. When you want to write or read data, you don't just trust one server. You need a certain number of them, that's the quorum, to all agree before the operation is officially a success. This is what stops you from accidentally reading stale data from a server that's a little behind the times. And this is where engineers get to play around and tune the system. They can adjust how many servers need to confirm a write, which is W, and how many need to respond to a read, R. If you make W plus R greater than the total number of copies, you get ironclad consistency. But hey, if you want blazing fast reads, you could just set R to 1. Or if you need writes to be fast, set W to 1. It's all about twisting these knobs to fit what your app needs. But what happens in one of those availability-first systems where you might have temporary inconsistencies? Well, you can get conflicts. To sort this out, systems use a really clever trick called vector clocks. Think of it like a family tree for your data. Every version of the data knows its own history, which servers have touched it and when. If 2 different versions pop up that aren't parent and child, the system knows something's up. It flags a conflict and asks the application, or maybe even you, to sort it out and merge the changes. You have to remember, at this scale, failure isn't just a possibility. It's a mathematical certainty. Servers will die, networks will go down, so the mark of a truly great distributed system isn't that it never fails, it's that it handles those failures so gracefully that you, the user, never even notice. So how does it do it? Well, for a temporary glitch, a healthy neighbor can just step in and take over for a bit. When the original server comes back online, its neighbor gives it a hinted handoff with all the updates it missed. Easy. But if a server is gone for good, you need something stronger. A process called anti-entropy uses a brilliant data structure called a Merkle tree to very quickly play spot the difference between servers. This lets it sync up a new replacement copy without having to send terabytes of data over the network. It's incredibly efficient. Okay, we've looked at all the individual parts. We've seen the theories, the tools, the tricks. Now let's put it all together and actually follow a piece of data as it makes its journey through a complete, living system. When you save some data, it's all about safety and speed. So first, to make sure it's durable and safe, the write is immediately logged to disk. Then, for pure speed, it's also written to a table in super fast memory. And then later, once that memory table gets full, everything gets flushed out to a highly optimized, sorted file on the disk. This combo gives you the best of both worlds. Your data is safe, and the write feels instantaneous. Now, reading data is basically the reverse, but with a fantastic shortcut. The system always checks that fast in-memory table first. If your data's there, great, you get it back instantly. If not, instead of just blindly searching every file on disk, which would take forever, it uses a clever tool called a Bloom filter. This thing can tell you with almost perfect certainty which files on disk might have your key, letting the system ignore all the rest. It's a huge time saver, and it's what makes reads so fast. So the big takeaway here is that behind every app that just works is this incredible hidden dance of complex, elegant solutions. The next time an app feels a little slow, or you have to pull to refresh to see the latest stuff, you'll know what's really going on. You're not just waiting on a slow computer, you are witnessing in real time that fundamental battle between guaranteeing perfect, up to the nanosecond consistency and providing constant, always-on availability. Thanks for joining me.